Welcome to Biogas Basics. My name is Jürgen Kuber, and in this presentation, I will talk about setting up a double membrane gas holder. If gas holders are not set up correctly, they can overpressurize, which leads to unnecessary flaring or even worse, venting. Venting is the dirty secret of the AD industry. Setting up gas holders correctly eliminates venting and is a necessary requirement for a sustainable AD plant. This presentation focuses on a single gas holder. The next will explore the interactions between multiple gas holders. This is a sketch of a digester with a gas holder. Biogas can flow in and out of the digester and it can be produced in the tank. Air is blown into the space between the inner and outer membrane and flows from this space via a pressure control flap. The pressure drop of the air flowing out of the pressure control flap is the pressure in the gas dome. The pressure in the air space, here shown in green, is almost the same as the pressure in the biogas space, here shown in orange. The difference is the weight of the inner membrane, which is around 1 kg per square meter, equivalent to 0.1 millibar. If the pressures weren't the same, the inner membrane would accelerate upwards or downwards, as per Newton's second axiom. We can make the following thought experiment. A gas dome operates at constant level. We slowly close the green pressure control flap and throttle the outgoing airflow. Further, we measure the pressure in the gas dome and the airflow through the throttle. We mark the pressure and flow pairs in a pressure over volume flow plot. The result is the characteristic curve of the blower, here shown in blue. When the blower is deadheaded, it makes 8 millibar in this example. When we open the flap completely, there is no pressure drop and the flow maxes out at 6,500 cubic meters per hour. Next, we keep the pressure control flap in its neutral position and vary the flow of air through the flap by ramping the blower up and down. The result is the characteristic curve of the pressure control flap in orange. At zero flow, there is no pressure drop, and at 5,000 cubic meter per hour, the pressure drop is 7.8 millibar. A system comprising a blower and a pressure control flap will operate at the intersection of the two curves. The flow through the blower is the flow through the flap. The pressure generated by the blower is the pressure drop through the flap. There are two ways to change the system. First, we can close the pressure control flap by adding more weights onto the flap or restrict the air outflow. As a result, the orange characteristic curve of the flap will get steeper. At constant flow, the flap will generate a higher pressure drop, and at constant pressure, less flow is required to achieve the pressure drop. We can also open the flap by removing some of the weights on the flap or open the air out at valves. The curve becomes flatter. We set the pressure control flap back to its original setting. The flow through the blower and the flow through the flap is 4,000 cubic meters per hour. The pressure in the gas dome is 5 millibars. Another way to manipulate the system is by slowing down the blower. Previously, the blower operated at 50 Hz. The blower speed has an impact on both the maximal pressure at no flow and the maximal flow at no pressure. We can reduce the frequency from 50 Hz to 25 Hz, and the blue line moves down and to the left. At 25 Hz, the system operates at around 2 millibars. Let's set the blower back to 50 Hz. Until now, we worked with a gas dome at steady state. The inflows were the same as the outflows. All produced biogas was consumed, and the gas dome level did not change. Now we are closing the biogas outlet and stop using biogas. The biogas can no longer leave the gas dome. Instead, it accumulates and pushes the inner membrane upwards. What happens to the pressure and the flows in the system? Let's assume that the biogas production is 3,000 cubic meters per hour. This is equivalent to a biogas production rate of 2,400 norm cubic meters per hour. Norm cubic meter refers to a reference state of 0 degrees Celsius, 1 atmosphere in dry gas. Because the gas is warmer, it expands, and it is also saturated with water vapor, which increases the volume under operational conditions. 1 norm cubic meter becomes around 1.3 cubic meter under operational conditions, i.e., saturated at 50 degrees Celsius. The inner membrane will be pushed up at 3,000 cubic meters per hour. The outlet flow through the pressure control flap is the sum of the flow through the blower and the volume displacement from the biogas. We can solve the problem graphically by adding the volume accumulation to the blower curve and check at which pressure it will end on the characteristic curve of the pressure control flap. In our example, the pressure increases to 7.3 millibar. This is above the opening pressure of the pressure relief valve, and the digester will start to vent. We will experience venting, even though the gas roof is not yet full, but because biogas accumulates in the gas roof. The pressure in the gas dome does not depend on the gas dome level, but on the level rate of change. The pressure goes up when the roof level increases and goes down, when the roof level drops. We can fix this in two ways. First, we can open the pressure control flap by removing weights from it. Now, the digester operates at 5 millibar while it is filling up, but in steady state, with no biogas accumulation, it will operate at the intersection of the two curves, slightly under 3 millibar. 3 millibar is still okay for the stability of the gas dome. The pressure in the gas dome should not drop below 2 millibar or the gas dome will start to wobble in strong winds. The second alternative is to leave the pressure control flap unchanged and lower the blower speed instead. In this example, the blower must operate at 33 Hz to keep the gas dome pressure at 5 millibar. If the gas dome stops filling and the blower continues to operate at 33 Hz, the gas dome pressure will be slightly under 3 millibars again. Now let's investigate what will happen if we take more biogas out than we produce. The maximal net outflow will be lower than the maximal biogas accumulation. The plant will always produce some biogas, and the net offtake is the total biogas offtake minus the biogas production or inflow of the tank. When the biogas dome depletes, the flow through the pressure control flap is the flow through the blower minus the net biogas extraction flow. The pressure drops from 5 millibar to 4 millibar in this example. If we want to keep the pressure at 5 millibar, the blower needs to ramp up to 57 Hz. If the blower were to continue at 57 Hz, but the net biogas offtake drops to 0, the pressure in the gas dome is 6 millibars. The variation of the blower speed is the better way to control the gas dome pressure, because it can be automated with a PID feedback control loop. Here are the steps to set up the gas dome properly for a gas dome without an air blower with a variable speed drive. Operate the plant at a steady state. The gas consumption must equal the gas production and the gas dome level must be stable. The gas dome should be approximately half full. The biogas plant should operate at target output. When all the requirements are met, stop the gas consumers and let the biogas accumulate. The pressure in the gas dome will go up. Adjust the pressure control flap so that the gas dome operates near its nominal pressure. This needs to be done while the gas dome is filling up but before it is full. Restart the gas consumers and check the gas pressure. It must be above 3 millibar to keep the gas dome stable in strong winds. If the pressure drops below 3 millibar, the blower is too small. If the blower has a variable speed drive and can be pressure controlled, use the following method. Same as last time. Operate at constant near nominal load with stable gas dome level near 50%. Set the blower speed to 40 to 45 Hz. Adjust the pressure control flap so that the pressure in the gas dome is at the nominal pressure, usually 5 millibars. Start the pressure control algorithm and parameterize the PID controller. Stop the gas consumers. Biogas will accumulate. Check that the pressure in the gas dome does not exceed the lifting pressure of the pressure relief valve. If this happens, the PID controller is too slow. Reparameterize with more gain. This concludes this episode about the correct commissioning of a double membrane gas holder. I hope you learned something new, and I see you in the next episode of Biogas Basics, where I will talk about the interaction of multiple gas holders in an AD plant.